G'day again, welcome back to the next video. Now, what we're going to have a look at today is what does the graph of a gradient function looks like? In other words, if you've got a function f of x or y equals some function of x, then what does the derivative function look like? Okay, so we're just going to have a look at these things today. It sounds complicated, but following a few sort of simple rules that we'll go through, this green table here, it's actually not as bad as you might think. I'm just going to flick over to Desmos, have a look at Desmos, and just have a look at a function. So I've just picked a random function here. So you see it's on the left-hand side there. Y equals 3x cubed, take away 2x plus 1. And you see that that function there is in red. Okay. And I've also just calculated the derivative of that, and I won't show it yet. I just want to sort of think about it. So the derivative of that function is 9x squared take away 2. All right. So I've just found the derivative, and I'm just going to sketch it. And so I'm going to put it there now. And so there it is now. And so that's in blue. That's the derivative function in blue there. I'll just zoom out. I'll just change it a little bit. I should have picked some better functions, but there they are. And so I'll just leave it like that. And I might just make it a bit bolder so it's a bit easier to see. Okay, so just a reminder, red is the original function, blue is the derivative function. And you might look at those and go, you can't see anything that's obvious to me about the relationship between these two, but let's have a look at them, okay? So I do want to zoom in a little bit though. I will zoom in just a bit here, okay? So first thing I want to show you is let's have a look at the turning point of the original function. So the turning point here, and Desmos is good because it tells us the exact turning point. And so looking at that, I'll have to hold on to it. The turning point of of the original function, it occurs at where x is negative 0.4714 approximately, okay? So 0.4714. And now let's have a look at what does that number represent on the blue line, which is the derivative. And so if I come down to the x-intercept here, have a look at the x-intercept, I'll hold on there. The x-intercept value of the derivative is negative 0.4714 as well, okay? So let's just check the other one. So the turning point of the original function is the same x value as the x-intercept of the derivative function. And that actually makes sense if you have a think about it, because when the derivative is equal to 0, then you'll get a turning point because it flattens out. But we'll talk about that a bit later, okay, when we get into functions. Let's have a look at the other side. The other turning point is here. Is it? Where is it? No, Desmos is not doing it. There it is. The other turning point occurs at positive 0.47 as well. And what's the other x-intercept? The other x-intercept is 0.47 as well. And so you'll see that if the original function has a turning point, then the derivative has an x-intercept. So I'm just going to write that in there. I found that piece of information. So the derivative function will have an x-intercept. Hopefully that makes sense. Let's go back and have a look at some other things. What about positive gradients and negative gradients? Let's just have a look at it. Where's my Desmos gone? Over here. Just get rid of all that garbage. Let's have a look at positive gradients. If the original function has a positive gradient, so you'll see in this section here, you have to have a look at my cursor, see I haven't got a highlighter on this screen, but you'll see where it has a positive gradient, so where my cursor is, that is all positive here until it gets to that turning point. You'll see that if the gradient of the original function is positive, then the derivative function will be positive. Obviously, the derivative is greater than 0, so it has positive. So you see that the derivative function is above the x-axis. That makes sense. Okay, then after this turning point of the original function, the gradient becomes negative. So it's negative all through here. It's going downhill, downhill, downhill until we get to the other turning point. So for this section in here, the gradient is all negative. And so you'll see with the derivative function is below the x-axis for all of this section in here. And so what we have is that we've got a negative gradient. That means the derivative function will be under the x-axis. And then for this last section, after the second turning point, it becomes positive again, and the gradient becomes positive for the rest of time. And you'll see that the derivative function is now above the x-axis again. So what does this tell us? Let's just go back to our little table. If the original function has a positive gradient, then the gradient function will be above the x-axis. And if it has a negative gradient, it'll be below the x-axis. And that gives us some important information when we're trying to sort of sketch functions. So let's have a look at this. I'm not forgetting about that last thing, by the way. I'll come back to it. Okay, so we're asked to sketch the gradient function for this particular function. And I just noticed I didn't actually label this, but this is y equals f of x there, okay? So there's that function there. So what would the gradient function look like? Let's have a think about this. I'm just going to sketch it to the right-hand side, and I'll do it in green so it doesn't look weird. So for this original function, it has a turning point at -2. I'm just going to talk about the x values here. X value of -2 and the x value of +1. Okay, so if we have turning points on the original function, that relates to an x-intercept for the derivative function. Okay, so what that means is that the derivative function is going to have at -2, it's going to have an x-intercept there, and also it's going to have an x-intercept at +1. So they're going to be my x-intercepts. Right, so that's my first piece of information. Let's have a look at the gradient of the function. So let's have a look. I'm going to just highlight where is the gradient on the original function. Where is it positive? It's positive from there to there. Okay, so that's where the gradient is positive. It's also positive over here from there onwards. So that's all the places where it's positive. So looking at my derivative function, it's going to be above the x-axis when it's less than -2. So it's going to be, up here somewhere. And it's also going to be above the x-axis when it's bigger than -1. So it's going to be up here somewhere. All right. Secondly, where is the gradient negative for the original function? Well, it's going to be negative in that area there. So it's going to be negative between -2 and -1. So it's going to be sort of like down here somewhere. Okay, so you can sort of start to get a picture of what the graph will look like. So the last thing I'm going to do before actually trying to sketch it is, well, what approximately is this function? It's got two turning points. It's probably a cubic. Okay, so that original function is probably a cubic. And so if that's a cubic, so it has it's something x, it's got x to the power 3 in it somewhere as the most powerful highest degree, then the derivative is going to be it's probably going to be a quadratic. Okay, probably going to be a quadratic. I'm going to say probably, definitely. So something x squared, because the power gets reduced by 1 with the derivative. Okay, and so we can sort of see what it's going to look like here because we know that. I'm just going to get rid of my squiggles now, and I'm actually going to draw it. We're probably going to see that the quadratic, it's probably a quadratic, comes down to here, and it comes up. I've missed the -1. Let me try that again. Comes down. It looks like that. And so that's probably what the graph of y equals f dashed of x looks like. Okay, we don't know for sure, we don't know specifics, but we know there's a turning point at -2, that's an x-intercept. It's got a turning point at 1, that will become an x-intercept. And we know that it is probably going to be a cubic going down to a quadratic, and so that's what the derivative will look like. Hope that makes sense. Let's have a look at this next question, and I'm going to go back up to that table we started with. State the values for which the derivative exists here. Okay, so having a look at this, and again, I haven't actually drawn, that's y equals f of x. I should label things. Let's have a look at this. This looks like a hybrid function where it looks like you've got a quadratic for this first section. That looks like a quadratic to me. And then there's another section here, which is a linear section there. And then it has a third section over here. I don't know what color I'll do it. Another section there, which I don't know. It's some sort of curve. It could be a number of different things. Could be hyperbola. It could be a root function. Who knows? It could be anything. Okay, so we need to find the values for where the derivative exists. Now, I'm going to tell you the answer, but I just want you to have a think about it. Where do you think the derivative won't exist? I'll just get rid of all my highlights so I can actually draw on this thing. If we have a think about it, along this line here, I'm just going to highlight. Along this line, the derivative exists along here, right? You're going to be able to find the derivative at all of these points, because anytime you draw a line on there, you can find the derivative there. That's going to be the the tangent to that. That's going to be, what's the gradient at each different point? The gradient there is going to be this. The gradient there is going to be that. We can draw a tangent line at any of these points. But have a look what happens when we get sort of up to here. What about that point there? What is the tangent at that point? Is it going to be this? Is it going to be that? What's it going to be? Like, we actually can't draw a tangent at that point 1, 3. That we don't know. There's no way to find the gradient at that exact point. Is it 0 because it's a flat line, or is it, is it 2 because it's up here? We don't know, and so it's actually undefined at that point there. It hits this point where the graph is no longer smooth. It's hit with, if I zoomed in on that point, it's like going up like this, and then it goes across. And so at that point there is not a smooth point. It's like a pointy bit, a barb. If you fell on it, you'd probably, hurt yourself. You'd bleed. So that point there is not smooth. Okay. Also, if you get to this point over here, we have a look at this point. What's the derivative at that point? Is it flat? Is it flat there? Well, we don't know, because also when x equals 3, we're also at this point here. And so again, what is the derivative? Can I draw a tangent line at that point? Is it, is it flat here? Or is it like that? Like, who knows? It's very confusing. It's not confusing. It's just undefined. And so the gradient actually does not exist at either of those 2 points. Okay, so I'll just get rid of all my scribblings and have a look at this much better. So what it means is that the gradient is not defined when it's not smooth and continuous. So at that point, that is not smooth at that point. So the gradient doesn't exist. The derivative doesn't exist at that point. This point, it's not continuous. The line is not continuous. There's this big gap between that point and that point, and so it's not there. So where does the gradient exist? So f dash of x exists for x, all real values, but not the points x equals 1 and not the point x equals 3. There, it's not defined for those 2 points there. Okay, hopefully that makes sense. So basically, coming back to my original table here, if y equals f of x is smooth and continuous, then the derivative exists. Okay. If it's not smooth, like a not beautiful curve, that's good. But if it's a and it has a pointy bit like that, if it's like that, then that derivative does not exist. So that's yes. That's smooth. That is not smooth. Okay. And if it's like this, that's continuous. But if it's lower and it has a break in it and a stop in it and it comes out there, that is continuous. That is not continuous. Okay. And so that's where the derivative won't exist. Hopefully that makes sense. I'll see you in the next video.